object in uniform motion tends to stay in that motion unless an external force is applied.
Yeah.
The relationship between an object's mass is acceleration and the force applied. Force applied equals mass times applied acceleration.
For every action, there's an equal and opposite reaction. We'll be demonstrating Newton's first law here, showing external forces acting on this tennis ball in two different ways. The first external force will be friction, acting upon this ball when we roll it. The object will also move in the direction of the external force, demonstrated here. Stated in Newton's second law, force equals mass times acceleration. The force will depend on the mass and the acceleration. So with the same acceleration, I'll first use the mass of a tennis ball. Now using the mass of a golf ball. Here I'll be demonstrating Newton's second law by showing the relationship with force equaling mass times acceleration by pushing on two different masses with the same force. Stated in Newton's third law, as you apply the force to the rock also applies a force back at you. Another demonstration for Newton's third law. The ball here will exert a force on the bat, while the bat exerts the same force on the ball, equally slowing down the bat.
Of motion states that an object at rest stays at rest, and an object in motion stays at the same speed and direction unless an external force acts upon it. And this is what happens on the kick example. Here the ball is moving towards that direction, but an external force, me, makes it go at the direction and speed I was going. We'll be demonstrating inertia. Inertia is the resistance of an object to motion. Here, the ball placed on top of the car shows little inertia as it went flying off as soon as the car stopped. This is described on the first law of motion, and it's one of the most important laws to take into consideration.
So for Newton's second law of motion, we had our first demonstration showing the acceleration's relationship with the force applied and the mass of the two objects, with the golf club having a net force on the golf ball and the tennis ball. The two objects had a change in motion with the net force exerted, and it went in the direction of the net force. And the net force caused a change in velocity, which therefore caused a change in acceleration. The golf club caused a change in velocity, which caused a change in acceleration. And the acceleration was dependent on the mass, so as you saw, it was relatively the same force applied with the golf club. So the tennis ball had more mass, so it didn't go as far, and the acceleration was not as much. And then the golf ball was smaller, had less mass. So with the same applied force, net force, it went a lot farther and had a much larger acceleration. So the more mass, there's more inertia with more mass. So with the tennis ball, there's more inertia, so it did not have as much of an acceleration. And the more mass also means less acceleration. And if the force is the same, so the force was the same with the golf club, which means there was less acceleration for the tennis ball, more acceleration for the golf ball. As you saw, the distance traveled also was affected. Now for our second demonstration, demonstrating Newton's second law, it was me exerting a force by pushing on the two objects, one being the car and one being the chair. Now this was similar to the golf club demonstration because it was a force exerted on two masses, one being larger than the other mass, one object having a larger mass than the other. But the difference with this one was that although there was a force exerted on the car, the car did not have any acceleration and did not have any motion because of the mass. The mass was so large that the acceleration was zero, so the mass times zero being the acceleration equals the force. So if you times the acceleration being zero, the net force would also be zero. So while there still was force being applied to the car, the net force was zero because the acceleration was zero. So yeah, the car had so much mass and inertia, so it resisted its motion, and the force applied the mass was too much, so there was no acceleration, meaning there was no net force while there still was a force applied.
In the example of a rock with the third law of motion being taken into consideration, we can see that as a human pushed the rock away, the force of the rock also created a push on the human. This is explained on the third law of motion, which states that push or a pull of an object results with the interaction of another.
So in one of our demonstrations demonstrating Newton's third law, I hit the tennis ball with the bat, so the bat was exerting a force on the tennis ball, but stated in Newton's third law, when one object exerts a force on another, the other object exerts an equal force in the opposite direction of the initial force. So the bat initiated the force on the ball, but the ball actually had an equal force on the bat in the opposite direction, which slowed the acceleration force of the bat down.